In the last lesson, we talked about uncertainties and how to express them with the measured values. In this lesson, we learn how to calculate uncertainties. In a lot of cases, when finding the value of a final quantity, it is often obtained by measuring a few other related quantities, which each have their own uncertainties. For example, when finding the volume of a cylinder or the extension of a spring under load. When finding the volume of a cylinder, we must first determine the cross-sectional area A, which is defined by pi over 4 d squared, before multiplying it with the length of the cylinder L. The volume is then given by this equation. Before we're able to find the volume, we must first know the diameter and the length. When measuring the diameter using a micrometer screw gauge or vernier caliper, the diameter would have an uncertainty of plus minus delta D. Whereas when measuring the length of the cylinder using a meter rule, the length would have an uncertainty of plus minus delta L. Likewise, when finding the extension of a spring under a load, we would first need to determine the initial length L1 and the final length L2. The extension is the difference between the two lengths. Since the lengths were determined by reading off from a meter rule, the lengths will have an uncertainty too. L1 will have an uncertainty of plus minus delta L1, whereas L2 will have an uncertainty of plus minus delta L2. From here, you can clearly see that the final quantities of volume and extension will require some sort of initial measurements which come with their own uncertainties. The overall uncertainty of these final quantities is called the consequential uncertainties, which would have taken into account the uncertainties of the initial measurements made. It is often obtained by adding together the absolute, fractional, or percentage uncertainties, depending on the form of equation that we're dealing with. Bear in mind that the uncertainties will never ever be subtracted, as consequential uncertainties will only ever increase and never decrease when more quantities are measured. This would make sense because when you do more measurements with uncertainties in them, your final measurements is only going to become even more uncertain. To find consequential uncertainty, it is important to recognize the form of equation that the final quantity is in. Take, for example, we want to find the consequential uncertainty of y. If y is defined as the addition or subtraction of other quantities like the one shown here, then we would say that the absolute uncertainty of y is equals to the absolute uncertainty of A plus with the absolute uncertainty of B. Say right now A is equals to 41.2 plus minus 0.1 centimeter, B is equals to 20.5 plus minus 0.5 centimeter, and Y is equals to A plus B. Y is thus equals to 61.7 centimeter, whereas the absolute uncertainty of Y is going to be equals to 0.6 centimeter. So the final answer will be 61.7 plus minus 0.6 centimeter. On the other hand, if the equation is Y equals to A minus B, then y is the difference between the two values, giving us 20.7. But the absolute uncertainty would be the same as before. So it won't matter whether the equation is an addition or subtraction of the quantities, the absolute uncertainties will always add up. Next, if y is defined as the product or quotient of other quantities, like the one shown here, to find the uncertainties, the absolute uncertainties will not be added directly, unlike the previous case. Instead, we will be adding the fractional or percentage uncertainties of the relevant quantities first, before we're able to find the absolute uncertainty. So if we have y equals to A times B, or y is equals to A divided by B, in fractional uncertainty form, it will look like this, where we say that the fractional uncertainty of y is equals to the fractional uncertainty of A plus the fractional uncertainty of B. If we were to multiply both sides with 100%, we would be changing it to percentage form, giving us this. In percentage uncertainty form, percentage uncertainty of y is equals to the percentage uncertainty of A plus with the percentage uncertainty of B. As an example, if y is equals to A times B, and A is equals to 10.3 plus minus 0.1 centimeter, and B is equals to 5.6 plus minus 0.1 centimeter, y is the product of the two quantities, giving us 57.68 centimeters squared, whereas the fractional uncertainty of y will be equals to the fractional uncertainty of A plus with fractional uncertainty of B, giving us the final result of 0.03. But this is not yet complete because we want to find the absolute uncertainty Y. So we will need to sub in the value of Y that we found earlier, which is at 57.68 centimeters square. So we solve right now to find out what is the absolute uncertainty, which gives us 2. So the final answer is thus 58.2 centimeters square. Earlier, we said that if Y is equals to the product or quotient of the quantities, to find the uncertainties, we will need to add up the fractional uncertainties. Along a similar line, if Y is still defined as the product or quotient of the quantities, but the variables are now raised to a power, we will still need to add up the fractional uncertainties. The only difference now is that the fractional uncertainties will need to be multiplied with the power to which the variables were raised, while bringing down the power and multiplying it with the fractional uncertainties. The reason for that is because when a variable is raised to a power n, it will contribute n times of the uncertainty towards the consequential uncertainty. For example, if y is equals to a power 3, b power 2, it can be re-expressed as y equals to a times a times a times b times b. So the fractional uncertainty of y would be equals to the fractional uncertainty of a added together by 3 times, whereas the fractional uncertainty of b will be added together by 2 times. So the final result that we will get is that the fractional uncertainty of y is equals to 3 times the fractional uncertainty of a plus 2 times the fractional uncertainty of b. Now, in the event that we have a negative in the raised power, we will normally ignore the negative sign. For example, if y is equals to a power 3 divided by b power 2, giving us a power 3, b power minus 2, we will just ignore the negative sign. If we were to consider the negative sign, it will cause the uncertainties to subtract. Recall that earlier I mentioned that uncertainties can never ever be subtracted, only added. So we will just ignore the negative sign here. The end result will be that the fractional uncertainty of y is equals to 3 times the fractional uncertainty of a plus 2 times the fractional uncertainty of b, which is the same expression as the previous example. Now, if we have a case where the raised power is negative 1, like the example shown here, y is equals to 1 over a, giving us a power negative 1, we will still ignore the negative sign and take into account the power 1. So the end result we will get is that the fractional uncertainty of y is equals to the fractional uncertainty of a. The last form of equation is a bit special. If the final quantity is a multiple or submultiple n of a single quantity, then the absolute uncertainty is multiplied or divided by n accordingly. If y is equals to n times of a, then the absolute uncertainty of y is equals to n times the absolute uncertainty of a. On the other hand, if y is equals to a divided by n, then the absolute uncertainty of y will be equals to the absolute uncertainty of a divided by n. Take for example, we have 4 cylinders that are laid side by side. The total length L is equals to 4 plus minus 0.4 millimeter. We are interested in finding out the diameter D of one cylinder. If L is equals to 4D, then D is equals to L over 4, giving us 1 millimeter. Since D is equals to L over 4, the absolute uncertainty of D will be equals to the absolute uncertainty of L divided by 4, giving us 0.1 millimeter. So the final answer of D would be 1 plus minus 0.1 millimeter. There is another way to go about this. That is by ignoring the multiple n and the submultiple n. If y is equals to n times of a, or y is equals to a divided by n, if we ignore the multiples and submultiples, we would say that the fractional uncertainty of y is equals to the fractional uncertainty of a. If we apply to the example below here, D is equals to L over 4, giving us 1 millimeter as before. So since we are ignoring the submultiple 4 here, the fractional uncertainty of D will be equals to the fractional uncertainty of L. If we sum in all the values and solve to find the absolute uncertainty D, we will get the result as 0.1 millimeter. So over here, you will be able to see that the answer is actually the same as the previous method. Next, let's review some examples. The first example says that there's an object measured that used the following reading. R1 equals to 20.55 plus minus 0.05 centimeter. R4 equals to 23.00 plus minus 0.05 centimeter. R1 is here, R4 is here. What is the length L of the object? We can say that L is equals to R4 minus R1. Notice that this form of equation is similar to y equals to a minus b, where we then say that the epsilon uncertainty of y is equals to the epsilon uncertainty of a plus with the epsilon uncertainty of b. If we apply it to this case here, we can say that the epsilon uncertainty of L is equals to the epsilon uncertainty of R4 plus with the epsilon uncertainty of R1. So if we now sum in the values, we will have L equals to 23.00 minus with 20.55, giving us 2.45 centimeter, whereas delta L would be equals to 0.05 plus with 0.05 equals to 0.1 centimeter. Recall that earlier I mentioned that absolute uncertainty must be at 1 SF only. So this is 1 SF and 1 dP. And the measure value must follow the dP of your absolute uncertainty. Since this one is at 2 dP, we would need to round this up to 1 dP. So the final answer would be L equals to 2.5 plus minus 0.1 centimeter. In an experiment, the external diameter D1 and internal diameter D2 of a metal tube are found to be 64 plus minus 2 mm and 47 plus minus 1 mm respectively. What is the percentage uncertainty of D1 minus D2? Bear in mind that right now they're asking us about percentage uncertainty. Before we proceed, let's assume that Y is equals to D1 minus D2. Notice that this is now in a form similar to this. If we apply it to this question here, we can then say that the absolute uncertainty of Y will be equals to the absolute uncertainty of D1 plus with the absolute uncertainty of D2. So now if we sum in the values, we will have Y equals to 64 minus 47, giving us 17, whereas delta Y will be equals to 2 plus 1, giving us 3. So our percentage uncertainty right now would be equals to 3 divided by 17 times 100%, giving us 17.6%, or rounded up to 2 SF, it is 18%. The formula for the period of a simple pendulum is T equals to 2 pi square root of L over G. Such a pendulum is used to determine G. The fractional uncertainty in the measurement of period T is X, and in the measurement of length L is Y. What is the fractional uncertainty in the calculation of G? Notice that the terms that have been used here all relate to fractional uncertainty. The fractional uncertainty of period T here is X, whereas the fractional uncertainty of length L is Y. And another thing to note is that the G that we're interested here is not the subject of the given equation. Before we proceed any further, we would need to make G the subject of the equation. So if T is equals to 2 pi square root of L over G, squaring both sides gives us T squared 4 pi squared L over G. Now making G the subject would give us 4 pi squared L over T squared. Now this form of equation is similar to Y equals to A power M divided by B power N, which we learned earlier is fractional uncertainty of Y equals to M times the fractional uncertainty of A plus N times the fractional uncertainty of B. Applying it to this question here, we can say that the fractional uncertainty of G is equals to the fractional uncertainty of L plus 2 times the fractional uncertainty of T. Now you may be noticing one thing here, that 4 pi squared has been ignored. The reason why it is ignored is because 4 is a number, it does not have any uncertainty to it, and the constant pi also does not have any uncertainty to it. So they are both ignored because they do not have uncertainties. So we proceed with the equation that we have. Fractional uncertainty of G is equals to fractional uncertainty of L, which we know is Y, plus 2 times the fractional uncertainty of T, which we know as X. So this would be our final answer. A body moves from rest with an acceleration of a traveling through distance s equals to 10 plus minus 0.01 meter in a time t equals to 4 plus minus 0.1 seconds. Given that s is equals to half at squared, calculate the acceleration and state the result as a plus minus the absolute uncertainty and then as a plus minus the percentage uncertainty. In this question, we want to find two forms of the uncertainty, the absolute and percentage uncertainty. And also note that the acceleration A is not the subject of the given equation. Before we can proceed further, we will need to rewrite A as the subject of the equation. So if S is equals to half at squared, then A will be equals to 2S divided by t squared. Now this form of equation is similar to this, where we say that if y is equals to a power n divided by p power n, then the fractional uncertainty of y will be equals to m times the fractional uncertainty of a plus n times the fractional uncertainty of b. So applying it to this equation here, we would get fractional uncertainty of a equals to the fractional uncertainty of s plus 2 times the fractional uncertainty of t. Notice that the 2 here has been ignored because this is a number. It has no uncertainties. So if we to sub in all the values right now, we will get A is equals to 2 times of 10.00 divided by 4.0 square, getting us 1.25 meter per second square. And then the fractional uncertainty will be equals to 0.01 divided by 10.00 plus 2 times of 0.1 over 4.0, we will get 0.051. Now, we want to find the absolute uncertainty as well as the percentage uncertainty. So one way we can get the absolute uncertainty now is by making use of the fractional uncertainty. We sub in the value of the acceleration that we found earlier into the fractional uncertainty. We will get the absolute uncertainty as 0.06. And then the fractional uncertainty, when multiplied with 100%, will give us the percentage uncertainty. So it will be 0.051 multiplied by 100, giving us 5.1%. So our final answer would now be A equals to 1.25 plus minus 0.06 meter per second square, or 1.25 plus minus 5.1% meter per second square. For our last example, the dimensions of a piece of A4 paper are measured using a ruler marked in millimeter. The results were x equals to 210 plus minus 1 millimeter and y equals to 297 plus minus 1 millimeter. Calculate the maximum and minimum values of the area of the sheet of paper which these measurements give. So now we have a sheet of paper whose dimension is x and y. To determine the area is actually the product of x and y. But right now, we want to find the maximum and minimum values of the area. A max will be equals to the product of x max times y max, which would then be equals to 211 times with 298, giving us 62,878. Whereas A minimum, the minimum area, would be the product of x min times y min, which would give us 209 times with 296, giving us 61,864. Lastly, express the result calculation of the area of the sheet of paper in the form of area plus minus the absolute uncertainty. The area is equals to the product of xy, which is 210 times 297, giving us the final result of 62,370. When we have a range of values, the absolute uncertainty can also be taken as half the range, where we take the max value minus the mean value divided by 2. So applying it in this case, our absolute uncertainty would actually be equals to the maximum area minus the minimum area divided by 2, giving us 62,878 minus 61,864 divided by 2, and our final answer would be 507. If we round it out to 1 SF, it will be 500. So this is now 1 SF, but rounded up to the nearest 100. So our area would be equals to 62,400 plus minus 500. Since we've rounded out the absolute uncertainty to the nearest 100, the measured value must also be rounded out to the nearest 100 too. To find the absolute uncertainty, we can also use the methods that we've used earlier. If area is the product of x and y, then the fractional uncertainty of A is equals to the fractional uncertainty of x plus with the fractional uncertainty of y. Subbing in the values, the absolute uncertainty of A divided by 62,370 would be equals to 1 over 210 plus 1 over 297. The absolute uncertainty would thus be 507. Notice that this is exactly the same as before, so we will be getting back exactly the same answer as the earlier method.